here, but somehow if you do not know a little bit more about this, I do not know how to complete this proof. Okay, so I will let me formalize this in a slightly cleaner way. For vertex cover, we can prove this very easily. Okay, but let's formalize this slightly more cleanly, and then it will be much easier to prove. Like just a one-line proof. Okay, and that is a kind of spirit of local ratio theorem. Okay, so okay, so this is a theorem which we can think of. And this is only for minimization problem. We can also prove, we will prove version for, okay. So let C be a set of feasibility constraints okay, on vectors in Rn. Okay, and let W, W1, W2 be element of Rn such that W equal to W1 plus W2. So basically these are feasibility constraints, like it should be vertex cover, for example, right. So this I can write down as a vector in Rn, right. Xu plus Xv should be greater than or equal to 1, or like some feasibility constraints, okay. Huh? Any kind of constraints, doesn't matter. Okay. Now let Xv in Rn, okay, be a feasible solution okay, with respect to C. Okay. Do you need precisely what to be meant by feasibility constraints? From the constraint. Okay, and be a feasible solution, okay, be a feasible solution with respect to C, that is R approximate, okay, that is R approximate with respect to W1 and W2, then X is R approximate with respect to W. Okay. So basically what happens, like you want to optimize some W dot X given some feasibility constraints, right. What is that? Oh, the set of things which I choose, like what kind of X we are looking for, which forms a vertex cover, for example, right. What are looking for? Some 0, 1 vector which forms a vertex cover and over which we would like to minimize. So this is my feasibility constraint, okay. Now what is the proof for this? Let x1 star, x2 star and x star be let x1 star, x2 star and x star be what you call, be optimum solution with respect to W1, W2 and W respectively, right. So basically in these questions what we have some cost vector and we want to W1 dot x. So what can I say about W1 dot x1 star? This is less than equal to, I can write it down as W1 dot x star, because this is an optimum solution. So its cost value and for minimization value can only be less than this, right. I can similarly write W2 x2 star is less than equal to W2 dot x star, right, because x2 star is an optimum solution which minimizes this vector W2x, right. So I could write my vertex cover as minimize over W dot x, where W dot x is nothing but, look, for every vertex I have a variable, should I pick him or should I not pick him, x1 to xn, and W is the cost vector, right. So this is the vector which I want to minimize, and I have a set, I have a constraints. What is the constraints? That for every u v edge, right, so this should be satisfied, that should be satisfied, and those are like constraints in R. If I had, like, what will I write? For each edge xu plus xv is at least 1. I mean, whether you are doing weighted version or unweighted version, how does it matter? Okay. So x1 star is an optimum solution with respect to W1. So clearly W, it is less than equal to W1 x star, and this is less than equal to W2 x star. Okay. Okay. Now let's look at W dot x, okay, which is a solution. Okay. Now W dot x is equal to W1 dot x plus W2 dot x, right, because W I can write it as W1 plus W2 and multiply with this x, it is just a dot product. Now what is this? What do we know about W1x, right? That is R approximate with respect to W1 and W2. So this is like R time W1 times x star plus R times W2 times x star. Now which is less than equal to R times, what is x1 star and x2 star, right, but this is less than equal to W1 times x star, not W1, what do they write here, yeah, plus W2 times x star, okay, which is equal to R times W1 plus W2 x star, which is R times W times x, right. So this is a factor R approximation. So I can think of my vertex cover algorithm as basically like this, right. So I decompose my vertex cover algorithm as I had two weight vectors, this is one W1 and this is W2, and I found an R approximate solution to this, R approximate solution to this, then I know that, like, so why it is an R approximate? Look at any solution here. If you go here, right, that's like, that's an R approximate because the only vertex which has a vector, which has any weight is these two guys, rest all are 0. Right. So basically you decompose your weight function one by one. So if I have to write this algorithm recursively, how will I write recursively, right? So this is how I will write recursively. And please note something important to note, okay? This theorem holds even when W is negative. I have never used the W is positive anywhere in my proof, okay, and this is very important. So now if I look into this framework, now if I want to apply this theorem to my vertex for, this is very easy, right? All I have to show that the two things which I decompose in W1, W2, I have got my 2 factor 2 approximation for that, and then it will give me a factor 2 approximation for this, okay. So here is my recursive algorithm, okay. algorithm recursive, say vertex cover, you give him G comma W, right? And basically what it does, at the end it will provide you a 0 weight solution. Okay. So basically what happens, if either we find a 0 weight solution or we find a suitable weight decomposition of my weight function and recurse on that weight function, okay. So this is the whole idea of local ratio theorem, okay. So now if I have to write, what will I say here? If min of Wu comma Wv equal to 0 for all edges uv, then what should I return? Return the set V, weight of V equal to 0. Clearly this implies it's a vertex cover, right? This is what I am returning. Else what I am doing, let U comma V be an edge such that epsilon, you define epsilon equal to min of Wu comma Wv, which is greater than or equal to 0, right, because we are not in this case. Define W1 of x equal to epsilon, right, if x equal to u or x equal to v, okay, 0 otherwise, okay. This is what my W1 of x is, okay. And what will be my, and define W2 equal to W minus W1, right. So I just defined you this, right. I know for these two vertices I am going to put epsilon and rest I am going to put 0, okay. And now what will I do? Return recursive Vc G comma W2, yes, W2, right. This is it. Now look at your W1, hey, any solution here is easy to prove that it is a factor 2 approximation, because these guys have same weight epsilon, right, and any solution will definitely pick this. So whatever solution I have get is what is the only two people who will contribute positive weight is this, and that's it. So if both I have got, I know I need at least epsilon, this solution will have weight 2 epsilon, right. And now inductively I would have got some solution from here, that's it, right. So this is a recursive nature of this. So I mean, so what did we get? Either we get 0 weight solution or we decompose weight into two suitable weight function. Okay, something to note. Right, look at W. First it becomes W1, W2, right, W2, W1 remains, I do not do anything. Now when I do W2, it can whatever it goes here, it can further change into something, right, and now this can further get changed into this. But if you look at the W of particular V, it is sum of all these weight functions, right, that property is always maintained, right. So this is an important something to remember, right, that basically this is a weight function which basically, like, this is exactly what I told you, right, it is like a pricing method, okay. I paid epsilon for you, so now your new weight is how much? Whatever weight minus epsilon. So this is what is remaining in the next stage. Oh, I paid another epsilon for you, so this is what is remaining at the end, right, till I have paid everything for you, okay. Okay, so this is what is called local ratio theorem, and you can prove that this is factor 2 approximation using induction, because in the base case any optimum solution cannot have more than weight 0, 0, right. So, I am giving you 0 weight solution. So, that is very trivial induction hypothesis, and I told you how to prove recursively at the end. Okay. And for the induction hypothesis you just apply this theorem, right. By base case W2 has a property that is a factor 2 approximation, all you have to show that W1 has a factor 2 approximation. So, take that same solution and prove that is a factor 2 approximation and you are done. Okay. Now, we will go back to matching. Look, I can do this for any hitting set problem, blah blah blah, factor 3 approximation for say like all the hitting problem for which I take all the 3 vertices or take 5 vertices. This is exactly how you will do the weighted version of this. Okay. 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 So, now let us go back to max weight matching. What should we do? I want to apply some sort of local ratio theorem here. Look, I taught you because if you do not understand this, there is absolutely no way you can understand whatever I am going to teach. Amazing, they explain very little sometimes. I mean, I could tell you the algorithm very fast. It's like it will take me just 5 minutes to tell you the streaming algorithm, but you will never understand why it is correct. I mean, of course, I will give you formal proof, but if you do not understand this way of forming something, it is, so how will I go about it? Right? I want to find a max weight matching. So, look, you can also prove a maximization version of this. It will be like 1 over something something, okay. You can also prove maximization version, but that is not the point, okay. So, I pick an edge, right, edges has weights. What should I do? What do you know about in any maximum weight matching? What do you know about this? You pick a positive edge, okay. Now, you know that from here, look at this edge and the edges which are incident to this, right. You have to pick at least one of these edges if I started with all positive weights. If I am looking for a max weight matching, right, and I have all positive weights to start from, I must pick one of these edges in my this, right. So, how do I want to pay for it, right? How do I want to pay for it? Suppose I pick this edge, I pick this edge, then I should reduce the cost from each of these guys, and that is it. Okay. So, by n of e, I will denote, my notation will be n of e will denote all edges incident on e, and n of e is n of e union e. So, this is just a notation. What happens if I just told you a weight function, right? think let us just do, this is the notation people are using, n plus of e, okay. So what I am going to do, I have done this, so I am going to take this weight function correctly and I am going to call w remaining, okay. This is just to follow the notation, it is not necessary to follow this. So I am going to define residual weight. So how were I defining this residual weight? I was only trying to tell you that hey, locally what happens and rest I do not care, right. So what will be this? I will say okay fine, if E is not in n plus of E, what I do? I just keep weight of A, okay. If E is in n plus of E, what do? I take weight of E minus, let us call this weight E star, okay, weight of E star. If E is in this, then this is what I do. This is all that I do. This is my new weight function, okay. So then what will be my corresponding W2 or WR is W minus WR bar. This is it, right. Now again I can say that look at the, what did change here? What did change here? There is an edge, right, whose edge weight has become 0, but notice some people could have become negative for all that I care. But that is perfectly fine, right, as I told you, right, my weight functions. So what did change? Hmm? So this is what I want to take, just to show the power. So suppose if I got a factor 2 approximation for WR, will that give me a factor 2 approximation for this? Okay. Let M be a matching such that W of M, sorry, WR of M, or and let M, so what is this? Say opt matching, okay. Let us call that M star is an opt matching with respect to WR, okay. M star is the, so what you know, and so weight of M star WR, like optimum matching, is less than equal to, sorry, I should not say, yeah, let us say WR, okay, twice WR max weight matching with respect to WR. So this is what I return MWR. What is a property? That with respect to optimum, optimum is at most 2 times this. So this is at least weight of this by 2. Okay. Now what happens? Maybe this matching contains one of these edges, right? Or it does not contain any of these edges. If it does not contain any of these edges, then I can take MWR and just take E star, right? Anyway, look, why could I pick this edge? Because none of these edges have been picked, right? None of these edges has been picked by this. So clearly weight of those guys are 0. And what is the weight of this guy? Like, so what did I get now? What I have got is a 0 weight solution. Do you get my point? Look at here, okay? So there are 2 cases. Okay, this looks a very clumsy notation, so I am going to use just R here, okay, MR. Okay, so what is the property? Okay, MR intersection N plus E is equal to empty. If this happens, then what I can do? I can take, if this happens, then I can take MR union E star. Clearly this is a matching. And what is the weight of this matching? Huh? What is the weight of this matching? This is 0 weight. It's a 0 weight. Because with respect to WR bar, this is a 0 weight. What did you say? Look. No, what stupid I did. 0. Otherwise it's not even a weight decomposition. Sorry. This is what I want to define. This is 0 and this is what it is. Them I am just putting my weight 0. The way for the vertex cover, the edge which I was considering, I was only looking at those vertices weights and putting every other vertex weights 0. Okay, WR takes care of the rest. I could do any way decomposition. This is my simplest way of decomposition. I look at this edge, any edge which are not here, I put its weight 0, right? Because they just do not exist through me. Because this is how I will propagate. And here I have given this. I mean, all this could have some negative weight, something, but this I don't know, okay. So what did I get? 0 weight. So, I mean, even if all other guys are 0, right, except maybe edges which are incident here, right, but hey, this guy did not, look, this guy did not, MR did not contain any edge from these guys. It did not contain. This is why I could extend this to E star. Otherwise, I would not have been able to extend to E star. So, what is the max weight matching now? What is this guy? I want to claim that with respect to, this is a factor 2 approximation with respect to WR here. What? This is now 0 for all E which is not in this. You are recursing on WR, not on WR bar. You are recursing on WR, which is W minus WR bar. So I decompose into a small, like simpler and non-trivial. No, wait, wait. This is a maximization problem. I shouldn't be doing this. Wait. I shouldn't be doing this. This is something stupid. So this is fine. I do this. Okay. I do this. Okay. Let's look at this. So I put 0 for every other weight. Okay. And for this, I just kept the same WE. Okay. E. So all these edges including E star gets the same weight as it is, and everything else here gets 0 weight. Okay, this is what it does.
But in WR you will be subtracting what is in WR bar, right?
Yes.
So then what are you doing? That for all the edges incident of them.
On this, all these guys are going to get 0 weight.
Yes, and the remaining will be the same.
Yes. Right, WE minus. So basically what happens, I have split my weights. So in one weight function I only give weights to these edges, and in other weight function I keep the weights of everyone else. That's it. This is what I did into my decomposition. Now what happens because of this decomposition, this is important to do this way, is now it's just a weight decomposition. I just like, what is your issue? So I'm trying to show you why it gives you 2 approximation, right? Okay. So now look, all these edges are present. All these edges are present, right? And now notice that we do not have this negative problem. I don't have any more negative problem. If I started with all positive weights, I will always be positive weights, even though it doesn't matter. I'm not subtracting anything. I just look at weights of some edges in one graph and look at all the other weights in some. So every weight is 0, greater or equal to 0. Right? In the next time, what will I do? I will look at some other edge. I'm never going to change the weight anything but 0 here. Okay. But notice one thing, but these edges are present, right? So I can always assume, first of all, look at MR, which is a max weight. Okay, MR is a max weight like with respect to say WR, like factor 2 with. So what is the meaning of this? Weight of M star R, there is some matching, is less than equal to twice weight of MR. Agreed? I can always assume that MR contains one of these, like contains one of these. If it does not, then you just pick E star. My max weight matching would, look, I already had max weight matching, I just added one more extra edge whose weight is 0. So this is perfectly fine. So if MR doesn't contain any edge from n plus of E, include E star to MR and get another factor 2 approximation, right? Because all those edges have weight 0 anyway. So MR always contains an edge. MR always contains, I can always assume either it contains E star or one of the edge incident to this. All I need to show that, look at MR, that's a factor 2 approximation here. And how will we show? Need to show MR is a factor 2 approximation, like MR means set of edges, is a factor, MR is a factor 2 approximation with respect to WR bar. That's all that I need to show. If I can show this, then I have given a decomposition where the same matching is a factor 2 approximation here, factor 2 approximation here, then with respect to W, which is W1 plus W2, which is WR plus WR bar, it is a factor 2 approximation. Wait, I think even this is not correct. I think this is what it is. Yes. No, this is what, this is.
Whenever you are subtracting, that is compensating for the negation.
No. So this is what it is, okay? This is what it is, WE star, okay? So this is what the weight factor is, okay? 0 for everyone else, and it is WE star if E is in this. Okay, so for all this guy, weight is same. Okay, for all these guys, weights are same. Okay, which is W E star for all these guys. This is now what if you look at your residual graph, we had 2, 2 here. Remember, whatever we reduced from each of these guys. Now we should be able to prove this. Okay, so now look at MR. I always assume that MR contains this n plus E. Why? Because if it does not contain any of these edges, then look at E star, right? Look at E star, right? I can add that E star to this and I still get because this guy has weight 0 in this, in WR. I am not talking about all these guys, right? I am only talking about this edge E star, it has weight 0 in WR, okay. And this is where it is okay even if weights become negative or positive, I do not care, okay. So what happened here? So now you gave me a factor 2 approximation, right? I could always add E star if you did not contain any of these edges. But now look at this edge, right? The only edges which has weight in this graph are these edges, right? Right? Okay. Now look at MR. So MR either contains this, look at this edge UV, right? Either contain this edge or contain, like either it contains this edge and not this edge. Then what is the weight of all these guys? Look, any maximum weight matching from here must contain one edge, right? Must contain one edge. Any maximum weight matching, right? So, and definitely MR contains one, otherwise we would have added it, right? So clearly, and rest of the weights are 0 anyway, so they do not contribute to my new weight function anyway. So whatever this MR is, with respect to this weight function, it is a factor 2 approximation because each of these edges has same weight, right? Each of these edges has same weights, okay? This is same weight, right? Look, weight of E star, right? So now what happens to with respect to MR? Either you look at an optimum solution. Optimum solution can contain 2 edges from here and everything else its weight is 0. So any optimum solution has weight 2 times WE star. Any optimum solution, optimum maximum matching in with optimum maximum matching with respect to WR bar has weight how much? Has weight at most 2 times WE star. Look at this maximum weight matching, right? Rest every edge is 0. You can add 2 edges from here in your maximum weight matching. Rest every edge has weight 0, right? So what is the total weight of that matching? 2 2 times WE. So that is the best you can hope for as a weight with respect to WR bar, right? And what I have given to you, at least one edge incident to this, right? So MR has at least, so weight R bar of MR is at least WE star, right? Sorry, WR bar E star. So this is a factor 2 approximation. Okay, so you have to decompose weights in the correct way. Okay, now I was making a mistake, like why I was subtracting it, I do not know. Right, so it's like, oh, whatever my contribution from everybody else is, let's remove. And what is the point? Let's try to understand what is the point. Look at this edge. Why did you not pick? So look, there are 2 reasons of not picking this edge. Look at any maximum weight edge, right? If you did not pick him, it means either you pick this or pick this, right? Suppose you pick both of them, both of these edges, both of them. Why did you pick both of these edges? Because if together they are less than this, then I can delete this and add this, right? So the idea is very simple. Look at this edge. Either optimum contains this or optimum does not contain this. If optimum does not contain this, then clearly optimum contain at least one edge here. Now why I cannot look, and suppose this is not saturated, because otherwise this is, if this is saturated and this is saturated, why I cannot add this edge at the cost of these 2 deletion? Because the weight of this guy and weight of this guy is more than weight of this guy, right? So any optimum solution must contain an edge with weight more than this, right? So subtracting it is okay from this. So like I am paying for the edges you will pick from here by dividing this cost, okay. Or what could happen? Even if you contain one edge in the optimum solution, why did I not replace with him? That is just because this guy weight is more than this guy's weight. So whatever edges is selected in my neighborhood, that guy's weight has to be more than me. Otherwise I can get rid of those 2, add myself and increase, right? So this is what. So it means the amount of weight which is used from my neighborhood is at least as much as me. So let me go and reduce my weight. So let me pay for that, and in the reduced graph find a maximum weight matching. Okay, so that's an idea. Okay. Okay. So this sounds like a good idea, right? I mean, it's an extremely good idea. Did you get this algorithm, right? And so inductively what changed here? Number of edges with weight 0 would change, right? Because once someone becomes 0, it never, does it change ever? Because look, I always change, it can get negative because I put a positive weight here.
Negative maybe we do not require the negative thing, because by this argument that you get, if someone becomes negative, that would not have been in the maximum matching solution.
We don't need to go to all that much.
Has to be greater than.
Yeah, but those are like going into arguments which we do not understand very well. So we should just, there should be some invariant which is changing like locally. We shouldn't care about it. This is the property of this local ratio theorem. It doesn't care about weights. So why should we care about weights, right? But something should change. Otherwise, why will this recursive algorithm will stop?
For every edge, you are doing it only once. With respect to every edge,
That's true, right? So this is why it will stop in m steps, and that's perfectly fine. Because if you are what am I doing? Okay, so this is an argument. I'm choosing an edge which has a positive weight, right? Once you become negative, you can only once you become negative, you can only become negative. So you will never be selected again. If you become 0 or something will never be selected. So this process will not, it will terminate in m steps, and that's it. So this is what I said, you do not have to argue anything in these kind of algorithms. It's like you have to just see what is the graph that changes. Like that's the beauty of local ratio. Locally I have maintained this ratio, I'm done. Yeah, it's decreasing, right? So, and I'm only choosing a positive weight is to reduce my weight function. So if everything became negative, you are done. What will you do at that point of time if every weight is negative or at most 0? No, why? At least at the end, if everything else has become negative, one guy will be 0. Yeah, so everyone else is negative, right? And this guy is positive, return that. Right? Or among all the 0 weight guys, find a maximal matching. Right? Negative guy is not going to contribute. Look, I will always have positive edge. Right? And I'm looking for a maximum weight matching. Right? I should never, like, I definitely look at the last transition. Some edge from positive will become exactly equal to 0, and no more I can do this operation. So I do have a positive 0 weight edge. Right? So what will I do? Okay, fine. Look at all 0 weight, negative edge, drop it. For the 0 weight, just find maximal matching. Right? Or you don't even care, you just return one edge. Right? That is also right. And the step where I go from here to here, I will make sure that, I mean, you're maximal with respect to the choices which you are making. That's it. So all you need at the end is, yeah, so why did you stop? Because all the weights has become 0 or negative, then just output one edge, and that's good enough, right? So that's a power. Okay. 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 Does this algorithm looks implementable? Right? Look what is happening. What are you doing in this? When an edge comes, when edge is picked, it reduces its contribution to all the edges which are incident to itself. But when we are doing incremental algorithm, some edge may come in future. But somehow if we can keep some potential which will remember, hey, when you come, you need to be deleted with respect to all the people who made the changes. Look at this guy, okay? I do this modification now here, right? But this guy is going to come in future, right? So his weight should decrease with respect to him. Okay, great. In this, now some other edge has done some operation. It should also decrease his weight. Some other guy has done something. It should also decrease. So somehow if I are able to keep this information that, hey, but so that whenever you come, I make you to like drop that, means then at this point of time I'm correct WR weight, right? And then I can do my choices. Okay. So this is what we would actually like to do in my algorithm, is somehow maintain these objects, like maintain some measure of my vertices which remembers all the weights of edges which has come before me somehow. But that is easy, right? For every vertex, just remember all the potential of the edges which comes. That's it. Right? Look, of course, I need implementation, right? But idea looks very cool, right? Fine. So I, as a vertex, I remember all the changes which had happened to me up until now. So when a new edge comes which is incident to me, I say, hey, I will transfer all my changes to you. Right? So if somehow we can translate this idea into an algorithm, we will be done, because this is exactly what this local search algorithm is trying to do. Okay? Okay. Do I want to say something more? Well, no. Okay. Let me tell you algorithm. I don't have much time. Okay. I would have also liked to tell you extended version of local search, but that's like, okay. So here is a cool idea. we are just going to implement this algorithm into streaming setting. And this is, as far as I know, this is the best known. We still don't know how to make it better than 2 for okay. Let's keep this picture, okay, and let's try to translate that picture into an algorithm. Okay, so I have an edge, okay, and this is going to come in future. Okay, so this is future, and red edges let's denote which has come already. Okay, so this guy is going to come in future. Okay, and so the changes which this guy can occur is all the edges which are incident to him. Of course, this guy has not come. So somehow I have to translate all the changes of these edges. So like what I mean by changes means in our algorithm, this guy had a positive weight and we tried to make change over that because we were anyway arbitrarily choosing an edge, right? And we were shifting the weight. Like what was the shifting? Oh, pick an edge, reduce its weights from everybody else which are in the neighbor. This is what was happening in WR, in residual graph. This is exactly what is, and rest we were doing nothing, right? And for the algorithm, we said, okay, this is basically like decomposing weight into this and keeping all the edges on this weight same WE so that it becomes very easy to see factor 2 approximation. Okay. So what this weighting matching algorithm is going to do? Okay, it's still I find it very non-trivial, but at least you know what it is trying to maintain. So maybe once you have an inspiration, one sees this algorithm. I haven't told anything. I don't know what I did, but so if something goes wrong, I have no clue. People are just, they will lose their job. So I guess they're recording it. This should be really thrown. Let's throw this out. I really don't like these things. Okay, so here is our weighted. This is like even worse. This is better. Okay, weighted matching algorithm. So I'm going to keep a subgraph. Okay, so it's like still a sketch from which we will say, hey, find a maximum weight matching in this, and that is good enough. But I mean, we don't even have to do those things, but we could do this. Like, look, anyway, it's a streaming algorithm. So if I can keep some sketch and say, hey, let's find a maximum weight matching on the sketch, and we're happy. But we'll be a bit more smarter. Okay. and this is a potential which we are going to store, and you will not see what this potential is till I go to the next board, which is 0. In the beginning, all vertex has potential 0, okay, for all v in V, okay. Now an edge arrives. I have to do something, right? Okay. For each edge ei equal to say u comma v, okay, right, and this is from e1, e2 dot 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 en. We have m edges, okay. So ei has arrived. What should I do? I ask myself, is it useful to take him? Okay. So how do I decide useful to take him? I say, look at the people who have done something to me. Look at the people who have done something to me, whatever that means, right? So this guy stores all the things which is done to him. This guy stores all the things done to him. If my weight is more than all the things which is done to me, I should be there, no? Whatever that all the, like, what I have been trying to tell is, look, if these are the potential edges, then if my weight is more than the potential set of my edges, then I should go in, right? Why should they go to maximum weight matching, right? So, okay, so let me write it down without 1 plus epsilon, okay, and then we will add plus epsilon something, okay. So I'm just going to say, if weight of ei, my weight is more than, strictly more than weight, not weight, phi of u plus phi of v, whatever I am storing, okay, then to h please add ei. Simple. Look, if, but now what should be my potential? Now if I did something to myself, I should add my weight, like register my weight to someone, right? But what is my current weight? Look, if I would have been doing my operation, my weight would decrease, right? Like this guy will decrease me, 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 this guy will decrease me. I should go and decrease, like add my potential for the future guys. What is my current weight? My current weight will be my weight minus the weight change which all these edges has done to me. Look at the step, right? You went and decreased my weight by 2. Someone else came, decreased my weight by 3. So my current weight is whatever weight I started with minus 5, right? So what is my current weight? All the weights you people have decreased and all the weights you people have decreased, and this is what I am storing in phi u and phi v, right? We will see in a minute, okay? And why? I mean, so if this is what, so now I have to update my phi u for my future, right? So what I do? I say phi u is phi u, whatever it is, and change, which is weight of u minus phi u minus phi v, right? Because at this point of time, I am calling my change. I am changing myself. It means, please, for future, go and add my weight to other people. And which is this is my current weight. That's it, right? Phi of v is phi of v plus weight of e minus phi of u minus phi of v. So this is what I'm going to change, add. Okay? Okay? And this is very clear why we are doing this, right? Everybody translates his future. So this is what, so if in the beginning if some edge will come, what is his future? It was 0, right? So it will add weight e, right? Next, so let's look at the 2 steps of algorithm, okay? So suppose first red guy came, this guy came, and this guy came. Let's just try to just do it, okay? So suppose this is u and this is v, and suppose this is 18 for now, okay? And this is like 3, 5, 7, 6. Okay. So what does U stores? Right? Suppose first 3 came, right? First 3 came, then what is phi of U at that point? Phi of U was 0 in the beginning, right? 0, so this is 0. Weight of A minus 0 minus 0. Okay. So phi of U is 3 and phi of V is 0. Just I am not worried about these things. Okay. Let's see phi of V. Okay. So clearly in future this edge also should decrease by 3, which I have stored correctly. Okay. Now 5 guy comes, but look, when I do 3 changes, right? When 5 comes, now 5 has come. So first 3 came, then 5 come. Now what does 5 should do? Oh, it has arrived. Now, I mean, like forget for now what we are going to do with this. What will 5 will do? 5 will do, oh, I should also update myself with you. But how much should I update myself? Hey, I already have been decreased by 3. So I should update you by 2. Right? Which is correct. At this point of time, this guy's weight should decrease by 5. Correct. Now this guy came 7. 5A is nothing, so he gets 7, suppose. Okay. But this guy is minus 1, so I would have not done nothing at this point of time. Look, my algorithm, that edge weight, whatever that edge weight is, right? If it is more than, then only I am doing something. No. But when this guy arrives, hey, this guy is 6, of course it is not. So I do nothing to it. Okay. And now my UB edge comes. What will I do? So this guy would have decreased him by 5. This guy would have decreased him by 5, 7. So 5, 7, 5, 12, residual is 6, which I should add to 5, 6. This is exactly what I am doing. Huh? Yes. 6. So this is exactly what my algorithm is doing. Right? So if because of some operation, some guy's residual become negative, we never consider that. Because phi u and phi b are positive objects. Right? The way we are doing it, phi u and phi b are always positive objects. Look, whether this algorithm terminates, whether this gives a factor 2 approximation or not, but it is definitely trying to mimic the algorithm which we just now presented. That's all that I was trying to show. Okay. Now comes magic. Okay. We are done with the algorithm actually. Okay. Construct a greedy matching. Construct a greedy matching in H, right? And greedy matching like in, oh, should I like add edge if you can add? It doesn't matter, okay? Because we were adding anyway greedy. If you notice, we were actually being greedy when we were doing bottom up, oh, add 0 weight. Oh, but if this edge you have saturated, why are you not picking it here? Okay, fine, let me put this edge, and we were going like that, okay? Okay, so construct a greedy matching in H by considering the edges in reverse order. Okay, this is for analysis. In the reverse order, they were added. Okay, they were added. Okay, this is for analysis because this is how I want to construct my matching so that I can analyze. But on H, I could have just done find maximum weight matching. That will not do worse than this, no? Look, this is the added, right? I added this, this. So now I add this edge first because greedy maximal matching. I added this. I said, can I add you? Why I cannot add you? I have like by considering. Okay, I mean basically it's a maximal matching which you construct from bottom to top. That's it. This is nothing more. You are not even looking at weights. That those guys have taken care of it. This is the whole point. right? You were basically doing greedy matching, right? Okay, weights were just forgotten. Okay. So let's prove that this algorithm gives you a factor 2 approximation. I'm not worried about how much space it takes, because this guy could very well end up using all the edges, keeping all the edges, right? So this is not a good, but I never promised factor 2 approximation. I only promised 2 into 1 plus epsilon approximation. This is what I like, 2 into 1, 2 plus epsilon, which is like 2 into 1 plus epsilon, right? 2 plus 2 epsilon, so epsilon prime is this, right? So this is not a big deal, okay? But let's first prove this. Okay, so let me prove this is a factor 2 approximation. Okay, so what I want to prove, this algorithm is factor 2 approximation. What's the time? Oh, we have 25 minutes, we should be done. Okay, let max weight matching has edges m star. Okay, I am talking about G. Okay, let m be the matching returned by our algorithm. Okay, and m is the matching returned by this process. So this returns m, right? Reverse, right? Now I'm going to define edge weights. Okay, and what I'm going to define, mi, you will see mi is m intersection E1 to M. Okay, so what is mi? It's an intersection with m from E1 to Ei to Em. So look, this is how edges are coming. Em was the last edge, but what I'm considering, if you notice, what I'm considering is, what is mi? Like intersection to Ey to Em, because I'm doing downward induction, because this is how we have constructed. Okay, and now I'm going to define weight function. What is a weight function of I? I'm going to define, this is very simply, weight of E, I will tell you what phi of U, if E is say uv, and phi of v. This is what my weight function is. Okay. Okay. But what is phi A? Here, phi of this is the value just before Ei was added. Okay, just before Ei is added, this is my phi I value. Okay, okay, just before Ei was added to the stream, right? So phi I is like, okay, up to this, after this stage, what was the value of my phi I? This is exactly what it is. Okay. Okay, now let's look at how wi plus 1 and wi changes, and this will open our eyes. Okay. Weight of edge. This is for analysis. Like algorithm is done, I'm not doing anything at all. This is for analysis. Okay, let's look at what is weight of I plus 1 times E. So let's go back to our, look at when edge Ei has not come, right? So what is phi, what is weight I plus 1? then E has been added to me, right? Edge E has been added to me. Now there could be two cases. Either E did something like EI was added to my H, or EI was not added to my H. If EI was not added to H, my weight of I plus 1 will remain weight of I. I do nothing, no changes to my graph because it is useless for me. But if EI was added, it means Y was added because it satisfies this constraint, right? And then I want to navigate whatever the changes happen in my graph, okay? So suppose in the case when EI was added to H, but look, I have defined what this means, right? So if EI was added, what will happen? If you notice, if EI was added, then phi I plus 1 u is what? Phi I u plus weight of EI minus phi of ui minus phi of v. Agreed? This is what, and similarly we can define phi I plus 1 of v is phi I of v plus exactly this quantity. This is what will, and nothing else will change in the world. If nothing else will change, then, so what is weight of I plus 1 is same if E is not adjacent to EI, right? Nothing will change because their U and V are not adjacent. Now, this is your EI, this is UV. If one guy is adjacent to this guy, what is going to change? If one guy is adjacent, then you will change. What is going to change? Look, this guy will drop him down. Okay, let me write it down what I mean by this. Okay. Then this is weight of E minus weight of EI. If E shares an endpoint with EI. Now why? Look at this guy, right? Look at this edge. What is this edge? What is weight of I plus 1 E? Is weight of E minus phi of U plus phi of some W, because this edge is say W, because it is only adjacent to one guy. Okay, sorry, what am I writing? This is what it is, right? But phi of I plus W is phi I of W, because nothing has happened to W. So this is equal to weight of E minus phi I plus 1 U plus phi of W, I times W. This is exactly. Now I know the formula of this. What is this? What is phi I plus 1 times U? Right? It is phi I U what did I do? Did I do something correctly? No. This is what it is, right? This is also minus, right? This. What is this? Minus phi I of U plus weight of EI minus phi I of U. Is it correct? Minus phi I of V. So this and this will get cancelled. Okay, that's not a problem. But what is weight of E? In the ith round, this is nothing but this plus this plus this. You substitute that, right? So because we are writing in terms of ith weight function, right. So what is WE in this round? It is nothing but weight of E, right, weight of E minus phi I of U minus phi I of W. Q? Oh right, this will go this side, right, this, okay. But now what happens, if you notice, phi I W and minus phi I W will cancel each other. Look, phi I W and minus phi I W will cancel each other, okay, and phi I V and not V, why it is V, okay, right. Yeah, this is fine, okay, this is fine, okay. So this and this will get cancelled, okay. Now this I can push inside, which is nothing but weight of Wi of Ei. Look, now phi I W and phi W got cancelled. This is equal to Wi of E minus, look, this phi of U I push him inside, so this is minus, right. So what will I get? I will get W of Ei minus phi I of V minus phi I of U. This is what I will get. But what is this? WEI minus phi of V is nothing but Wi of E. So this is what you will get. But am I getting EI? No? Yeah, this is exactly what it is. Right? This is, if you think mentally, this is much more easier. Right? What has happened? Wait, now this guy is going to remove his share from him, and this is exactly what it is, right? And what is his share at that point of time? This is his share, no? So why are we worried? I mean whatever computation we do, this is like I just did it for your sake, but what is he doing? He is going to deduce his weight. What is his current weight? This is his current weight. So he is going to subtract that from him. This is what he is going to do. That's it. So I mean, what's a big deal? And what is this? If E is not adjacent to Ei, and what is Wi of E if E equal to Ei? It is going to be 2 times Wi of Ei if E equal to Ei, right? Because both end is going to subtract from him, no? That's it, okay? If Ei is added to H, otherwise Wi plus 1 equal to Wi. This is basically weight decomposition at Ei. With respect to Ei, I have done the weight decomposition. This is all. So think of each Wi is like my weight, current weight that got decomposed, that got decomposed, that got decomposed. So this is basically we are following the line of argument of our algorithm. Okay, excellent. My God. So what I want to show, okay, want to show Wi of m star is less than or equal to twice Wi of m. Mi for all I. Okay? And how? By induction or decreasing I. This is what I want to show. If I am show this, will I be done? What is W1? is weight of E, right? So then we will be done. See, if I can show this using induction, then I will be done, because, okay. So let's try to do this. I mean, we are done. I mean, like, once you set up everything, it's nothing. Okay. Base case, what we have to show? Wm of m star is less than equal to Wm of mm. What is mm? One edge. Okay. At this stage, what happens? And except this edge, possibly every edge has weight 0. At this stage, look, what is this? What is Wm? Is hair. What? Look, if there was any positive weight at any point of time, you would have added in your h, no? No? Okay. So my claim is that this is what I want to show, 2 times Wm, right? I claim to you Wm of E equal to 0 for all E except possibly Em. This is my claim. Look at your previous algorithm, no? When did it stop? And what is this? I am just doing the same algorithm, no? So at that stage, the only possible edge which we can have non-zero weight, because what is Wm? We minus phi m minus, like, what is Wme? Is We phi mu minus phi mv, just before this edge has been added, and this is the last edge of my graph. I have processed all the edges in my graph. This is my last edge, right? So this guy could have possibly have positive weight, except everyone else has a 0 weight, right? And then I am perfectly happy, right? Because what is m star? M star could either contain this edge, last edge, or all other edge in M star has weight 0 except maybe Em, but Em is also present in mm, no? So this is perfectly valid. Okay. Interesting is induction. Okay. Okay. So now we will prove it for some I. Okay. So first case, it's easy. If Ei is not in H, then what can we say? Ei is not in H. Then weight of I plus 1 is weight of I, because if I did not add I plus 1th edge, then my ith weight is same as weight of I plus 1, right? So now it is very simple, right? So weight of I plus 1, sorry, weight of I of mi is same as weight of I plus 1 mi right, because anyway if this edge is not added to H, it is not added to my M also, right, because I am only finding, or maybe the right way of writing is not this, let me write out weight of I of M star is equal to weight of I plus 1 of M star, which is less than equal to, right, which is less than, now I apply induction hypothesis, which is 2 times weight of I plus 1 of M I plus 1, right, which is equal to 2 times W I plus 1 M I, because they are same, right, which is equal to 2 times W I M I, and we are done, right. Okay, if H was not added, everything remained same, good, excellent. Okay. So this is 1 volt. Okay. Else, now we are assuming that EI is in H, right? It is in H, otherwise it does not make sense. And let N be the set of edges incident to EI. Agreed? In G. Okay. Now what do I have to show? Weight of I of M star, right, is less than equal to, I will use this fact, look at weight of I of M star, I claim this is equal to plus what? Twice WI, right. I could have picked this edge itself in my solution, right, sorry, this edge itself in my solution, right. So it is just the last edge, right, which, so this is 2 times what is this, 2 times Wi, no, from here, 2 times, we are done. No, what am I writing? This is stupid. This is what it is. Look at your M star, its intersection in M star, and now look at an edge, right. Now how much edge that weight matter, right. Look, I might have added EI to my solution, right, M star, look at your weight of M star, whatever its weight in M star, and maybe some edge which is incident to him had changed his weight, but how much from weight of EI? Just twice. So this is why twice, right, because from here you can just get 2 edges at most. So if you get 2 edges, then if you had 2 edges incident, then this guy will add WIEI, other WIEI. If you added this edge, it's 2 WIE, but this is what you will get. Excellent. But here I can apply induction hypothesis, right? Here I can apply induction hypothesis that this is twice Wi plus 1 M I plus 1 plus 2 WI EI. Agreed? I am not doing anything else. This is all that I am doing. So this is an upper bound on my M star. Now if I can show a lower bound of this, then I will be done. Agreed? Okay. And since Mi has at least one edge incident to N, Do you agree to this point? Right, because at least EI was present, right? When I am doing this reverse thing, I mean, look, how can you, if no edges of n was present, you could have, then you would have taken EI at least, okay? And hence what happens? Look at weight of Mi, this is at least weight I plus 1 right. Look at any Mi, right, it definitely contains all these edges, right, and now it contains an edge incident to like from n, then that guy's weight will increase by this much, no, in I, like one of this edge, right. So weight in Wi is this plus some increase, at least this much, maybe not this much, but at least this much, Wi plus, yeah, this is what it is. Now what am I writing here? This is correct. Look at any Mi, look at its weight in Mi, in I plus 1, right. I am just trying to, its weight in Mi plus one of the edges incident to n had changed his weight by Wii. So this is why it is. But this is greater than equal to Wi plus 1 Mi plus 1. Why? Because Mi plus 1 contains less edges than Mi, may contain less edges, right. So I have given you a lower bound on Wi Mi of this, which implies now if I put together these two inequalities, what do I get? If I take this, then I will get twice 2 times Wi Mi, right, and this is what I was trying to prove. Right. So this is great, okay, but this gives you a factor 2 approximation, and to make it n poly log n, we are going to add 1 plus epsilon here. Now what happens because of this? I added just 1 plus epsilon extra, right. I said, look, I am not going to take you when you are strictly greater than, but you are at least 1 plus epsilon times greater than, only then I am going to take this edge, okay. Then notice what happens, look at first time the value of phi, it is at least 1, next time it will increases by how much, at least by 1 plus epsilon. So if I assume that I have 1 plus poly n, right, like weights are between 1 to poly n, how many times can this increase before this phi u cannot increase? Look, if phi u value is more than any edge weight, it cannot increase any more further, right. So it means what, at every time step, like, so every vertex phi u changes how many times, some log 1 plus epsilon times n, like 2 times log 1 plus epsilon times n, okay. So with this modification, right, at most log 1 plus epsilon, okay, poly n edges are incident to any vertex V in H, right. So we will get n poly log n, right, great, right. But how do we analyze that this is 2 into 1 plus approx? We will be a bit more clever, we just reduce our reduction to this, which they do not do it, but we can do it, okay. I mean, I do not know why they do that in paper, but fine. Here is a simple trick, okay. So I am going to define a new weight function, so this is okay, right. So if I give you a weight function such that if I can reduce the previous construction, means I have to give you a weight function where adding an edge becomes like, oh, add with respect to that w prime is at least this much, that will give me a factor 2 approximation, and then I have to do something. Look, analysis of algorithm is done. All I have to say that, look, you come up with another w prime and you take your edges with whenever this is greater than this quantity, then that will give you with respect to that w prime this, okay, and that is very easy. So, I am going to define a new weight function, okay. It is my class at 4 o'clock. Huh? Oh, you have 3:30 LPCO? 5 minutes, 2 minutes? Okay. So, you will just understand, then I will do. So, I'll define a new weight function w prime, okay, as follows, and we'll run this algorithm with this w prime, okay, and your epsilon is greater than 0. So, w prime of E, if it is between some range, okay, then I will do something else, okay. So, what it will be, I will make WE 1 plus epsilon if w prime of E is WE but less than equal to 1 plus epsilon times WE. No, what I am saying, no, what, oh, no, this is not what I should be doing. If phi u plus phi v, so this is the weight function which I will define, and I will do with respect to this weight function. So WE is greater than this, but it should be less than equal to 1 plus epsilon times phi u plus phi v, okay. Yes, okay, then you define this, otherwise you define weight of A, okay. And now you run the algorithm, what will I say? Add to H, if, now you go, you will be able to figure out from here, okay. Add to H if w prime of E is greater than equal to phi u plus phi v, right. This is same as saying what? Add to H if this happens. So, which is same as add to H if w prime E is this. So, either this happens, which is perfectly fine, or if w prime of E is more than 1 plus epsilon times phi u plus phi v, right. I am running this algorithm with this, and that is it. So, now what will I get? Okay. So, we know using the first rule, finds matching. What is the property of matching? So, it finds matching M, w prime M, which is greater than equal to w prime M star divided by 2, right. Like, yeah, like with respect to w prime, let us call it M w prime, just, okay. This is what it will find. So, if M w prime star is a max weight matching with respect to w prime, not with respect to w, this is what guarantee I can get from the previous algorithm, right. Here M w prime are M w prime star are the edges with respect edges in optimum weight matching with respect to w prime, okay. Okay, but now let us see what happens, right. Okay, great. Now we will convert this with respect to M. So what is W of M, weight of M, because this is what, so I am going to just return this M, okay. Weight of M is definitely greater than equal to W prime of M, because what have I done? Hey, look, I could have decreased the weight because epsilon is greater than 0. So clearly this statement is true. But what is W prime of M? is greater than equal to w prime of m w prime of m w prime star divided by 2. Okay, is this correct? Okay, but this quantity is at least, at most or at least, wait, hold on. Is this correct? No, I am not looking at say MW is an optimum matching with respect to weight W. Look at their weight. Like, and why this is true? Because this is an optimum weight matching with respect to W prime. So this guy can only be larger than this. Look, I am looking with respect to W prime weight. MW is an optimum edges of optimum weight matching. Look, are the edges in optimum weight matching with respect to W prime. What is MW star? MW star are edges in optimum matching in G with respect to W. This is what MW star is. Now you look at the corresponding edge and look at weight with respect to W prime. What was this guy? This guy was optimum weight matching with respect to W prime. So clearly that guy's weight is going to be good because this is a matching here. Do you understand this point? Look, this optimum edge matching in G are also matching edges in this, but I am applying a different weight function. So optimum could only be different, right? So this guy is not only W prime, it is a set of edges which is optimum with respect to W prime. This is some other set of matching edges which may not be optimal with respect to W prime. Look, it is still W prime here. W prime matching. This is best matching weight, this is some matching weight. That's it. Okay? But now we are done. This guy, I want to replace, what is this? I have some lower bound, right? Look, okay, look at any, I want to say this is at least greater than equal to W MW star divided by 2 into 1 plus epsilon, which follows because of this. That's it, right? So now you are done. That's it, it's over. Okay, so this gives you a factor 2 approximation, and I don't think there is anything better known for this.